Hello everyone present here. First of all, I would like to thank you all for attending this presentation. I am Sarthak Chakravarti and I currently work at Adobe Research India. My advisor Sandeep Chakravarti and I worked on this project titled Proof of Federated Training, Accountable Cross-Network Model Training and Inference during my undergraduate studies at IIT Kharagpur. So let's get started. Federated learning has become a very popular paradigm for learning a model in a distributed fashion. It is getting deployed in various large-scale network systems as well, like Google Keyboard and NVIDIA Clara healthcare applications. So, how does a typical FL setup looks like? In FL, there exists a server that maintains a global model, and whenever clients are ready to train, the server sends the global model to all these clients, where each client trains the model independently on their local dataset only. The clients then send back the model to the server that aggregates them using some aggregation strategy and update the global model to a new version. This entire procedure runs in iterations, and such a framework is useful to collectively train a DNN model without explicitly sharing the local data. However, to improve the security of the FL framework, works have been done to provide accountable FL architectures where the version of the global model are audited over a distributed public ledger. The clients collectively execute the server as a service over the blockchain in a decentralized FL architecture. However, for cross-silo FL applications, these decentralized FL over blockchain do not scale since organizations running FL clients are a part of independent blockchain networks. However, these silos contain data from the same domain, which can be leveraged to train a richer model without explicitly sharing the data across silos. Some use cases of this application include in the medical domain where a rich disease diagnosis model can be developed. Other use cases exist in the agri-tech domain to run a yield prediction model based on data from different silos, or in the banking sector for credit card fraud detection. A concrete example of the use case is shown where a group of hospitals use a service like Clara Medical Imaging over a blockchain based decentralized network to train a model for personalized recommendation. Another group of diagnostic centers use Clara for endoscopy, where these centers form another blockchain network. Now, a model learned on endoscopy imaging data can be shared across the silo for a richer model to be learned for clinical diagnosis in the hospital. However, since the two silos are different and not under the same organization, there is a reluctance to share the complete internal data, but only a part of the data or the model learned is permissible to be shared by maintaining appropriate privacy. Hence, the question is, how can a Clara FL model be trained over both the silos jointly? To share the model across multiple blockchain networks, some of the primary requirements are 1. Every blockchain network should be able to independently verify the individual version of the global model received. 2. The transfer across the network and the end network update of the model should run asynchronously. And 3. The cross-network transfer protocol should be Byzantine safe. Though there has been partial solutions for some part of this problem, but there lies a gap in a complete end-to-end solution taking care of all the requirements. There has been some previous researches on this front. These methods use blockchain as a separate service over the FL and have architectured their system to work reliably using a single blockchain network. There also has been many works on blockchain interoperability involving different blockchain networks. However, they suffer from at least one of these shortcomings. The assets they use to represent the learning model are either not verifiable, or even if they are verifiable, is not able to verify independently from other versions of the model. And there has been a significant dearth of research for cross-chain FL, and the systems for interoperability are not optimized for cross-chain FL training. In this work, we aim to overcome these shortcomings and develop an end-to-end cross-chain scalable federated training framework over multiple blockchains named as Proof of Federated Training (POFT). It decouples the model update from model verification and thus an asynchronous updating of the models and running of blockchain services. It uses model parameters to create a verifiable representation of a DNN model as a learning asset and enables a seamless cross-chain transfer verification protocol. So to set up the problem, we define two independent networks N1 and N2 that independently run and maintain their own permission blockchain networks B1 and B2 respectively. to train a DL model using decentralized FL. Each of these networks has a set of enterprises as shown that run the FL client service over their respective blockchain. Now, the objective of POFT is to transfer the learned global model from clients of N1 to clients of N2 by leveraging the idea of interoperability between B1 and B2. So, in bird's eye view, a learning model will be trained in a decentralized FL setup over a blockchain, and at each iterations, the global model state needs to be stored in the public ledger in the form of an asset. Now, how the asset will look like or what information must be kept in this asset will be touched upon in further slides. To make the cross-network transfer of assets asynchronous from the in-network update of the model, a separate process will keep a track of whether the request for transfer has arrived or not. And if a request has arrived, the appropriate asset is retrieved from the ledger and will be signed for verification and auditability at the signing end and will be transferred to the requesting network. On the receiving end, the asset is verified following a verification protocol and stored in its own local ledger. The model weights or parameters can then be used as required to train the respective model in the second network. Now let us look at how an individual network looks like in our system. A set of enterprises will act as FL clients that maintains their own local data and will train the DL model. The clients are connected to a blockchain platform and fetches the latest version of the global model from the blockchain to train. These local models are then forwarded to the blockchain and the aggregation server contract is triggered to aggregate the local models. Now, PFT uses a federated averaging algorithm for model aggregation, although any aggregation method can be used. Once aggregation is performed and an aggregated global state is formed, the global model is then updated with it and is represented in the form of an asset into the blockchain. However, clients and the aggregation server contract needs an ordering service over two-way communication, since the smart contract needs to update the global model after the clients forward their local models, and similarly the clients should start the next iteration once an aggregated global model is generated. Hence, to synchronize these operations, we use an ordering service as an event streaming platform in a publisher-subscriber setting for ordering different versions of the model. The clients will publish the local models using the streaming channel, and once a requisite number of models are received, the aggregation server contract is triggered. Again, when the update is complete, it is published over the streaming platform, and now FL clients can subscribe to the stream queue to retrieve the model. Now, after training the model on N1 and before transferring the state of the model to N2, we will need to answer what that state refers to or what can be stored in that state. The state is what referred to as an asset, and we represent a partially or fully trained model in this asset. However, we'll need to ensure that whatever information is stored in the asset representing the model, it should be fully sufficient and independent of the previous versions to verify the auditability of the learning model. To do this, existing works have represented the structure of the neural network as a state machine by representing each neuron or each layer of the model as a separate state in the blockchain. We call this technique as the structural embedding of the model. Though there will not be many issues with the verifiability, but such a formulation becomes infeasible with increase in the model size. Since increase in the model size means increase in the number of layers, and hence the structural embedding to represent the asset can become intractable for larger models. However, in POFT, we use parameter embedding to represent the state of the global model. The model weights or gradients that were learned by the model during the FL training used as a representation of the asset. To demonstrate the advantage, we show a pilot study where we have trained two CNN models for an image classification task on CIFAR-10 dataset. The characteristics of the model are shown in the table, and insert time is a time taken to create the asset and insert the asset into the blockchain. From the table, we see that the structural embedding cost significantly higher in terms of asset size and the time required to insert the asset into the blockchain. Since the parameters can be shared over a few activations and layers, it becomes implicit that the parameter embedding greatly reduces the asset size. Though parameter embedding is the most suitable choice for representing the model and storing its state in the blockchain, there lies a conundrum. The parameters learned during an iteration displays only partial information and cannot alone ensure verifiability. Therefore, an additional information must be included with the asset structure to verify that the model weights and gradients indeed provide a correct representation of the model. Hence, the idea is to use the standard logic of model validation for verification purposes. The network will use a public validation dataset and store the metrics as observed corresponding to this validation dataset. Not only are the metrics necessary for proper verification, but the asset needs to store the model parameters, the model hyperparameters, the random seed used, the optimizer and the loss function used, as well as the pointer to the validation dataset. The structure of this asset is as shown in the figure. So now we come to the cross-chain transfer architecture. And before we dive into the specifics, I want to point out that we assume the existence of an identity interoperable network as a blockchain service which helps the clients to access the public keys of the clients from other networks. PFT uses a relay service which is run as a service by one of the networking clients that acts as a mediator throughout the transferring of the assets. So the steps are: 1. The client E1 of N1 requests a version of the global model from network N2 through the relay service of N1, and the destination address is obtained based on the identity information present in the clients as assumed. The relay service of N1 then serializes these messages received from E1 and send it to the relay service of N2 via HTTP post request, where these are decoded to extract the parameters. Next, the relay service of N2 then initiates a transaction to B2 to access the required version of the global model. The transaction goes through the local blockchain of consensus of B2 to prevent the relay from exhibiting any Byzantine behavior. The blockchain B2 then triggers a local service via a smart contract, and through this service, the requested asset passes through a Byzantine agreement based on the signing protocol. Finally, the relay of N2 communicates the signed asset to the corresponding relay of N1 along with the verification credentials. And after Byzantine agreement to verify the received asset from N2, the client application E1 updates its learning asset to the blockchain. And for the signing procedure, we follow the well-known collective signing or COSI protocol. Signing ensures that the asset can be verified that it was not corrupted or was sent by a trusted blockchain. In COSI, the majority of the peers collectively sign the asset using the BLS crypto system. The clients who sign the assets are termed as witness cosigners, and the relay service asks the peers to sign the asset that needs to be transferred. After each of the peers signs the assets, a multi-signature signed asset is formed. BLS signature is extremely fast and scalable and have a special property that makes the calculation of multi-signatures very easy. Thus, a signed asset is transferred. Now, at the verification end, the protocol needs to verify two quantities. 1. The received learning asset has passed through the COSI based Byzantine protocol from N2, and 2. The asset contains the correct model parameters. For the first requirement, the clients use the identity interoperable network to retrieve the public keys of the clients who have signed the asset and use it to verify the signature. For the second, the clients use the public validation dataset to check the model reproducibility. As earlier said, the asset contains a pointer to the dataset, and hence it can be used to verify the correctness of the model weights transferred. This completes the architecture of our PFT system, and now we will move on to the evaluation sections. For the implementation of the blockchain, we have used Hyperledger Fabric, and we have implemented our system in AWS EC2 instances where the clients and the Fabric server are run on separate Docker containers, and multiple instances were connected to each other via an overlay network. We have used HTTP request response protocol for cross-chain communication, while Kafka is used as an event streaming platform. An important point to note is that Hyperledger Fabric SDK limits the size of the byte arrays encoded in a single transaction to around 1.2 megabytes. However, the size of the learning models we use are comfortably over 1.2 MBs. Hence, we break a learning asset into multiple fragments of size 800 kilobyte each, and we enter these individual fragments into the ledger with separate IDs. It must be noted that while retrieving the asset during the cross-chain transfer, all the corresponding fragments are retrieved and stitched together before signing and transfer. For evaluating the FL system, we have used CIFAR 10 dataset containing 50K training images and 10K testing images. So the 50K training images are divided among different clients following an IID distribution. And for evaluating the efficacy of the transferred model weights, we use CIFAR 100 dataset with 20 course classes. The FL training task is an image classification task, and we have used 4 different models to evaluate the performance of POFT. First, we use a simple CNN model having a 6-layered convolution layer followed by a dense layer. Next, we use a compressed version of the VGG using 7 layers where the convolution kernel is replaced with a file module inspired by SqueezeNet. We also use the MobileNet and the ResNet, both being popular large-scale CNN models used for practical vision applications. To record the intra-chain FL performance, we use a global test set as well as the local validation set at each client. We evaluate the aggregated global model and is represented by suffix pre, as well as the local trained models as represented by suffix post, which are averaged over all the clients. To analyze the overhead during cross-chain transfer, we report the latency incurred to create the asset retrieval time, the time needed for COSI based Byzantine agreement, and finally time for model verification. Additionally, to the best of our knowledge, POFT is the first of its kind to propose a cross-chain model training framework, and existing works are not suitable in this regard, and so we do not compare the performance of POFT with other approaches to avoid unfair comparison. In the first set of experiments, we show the performance of FL system where we employ 10 and 40 clients. From the graph, we observe that the pre-test accuracy is higher than the post-test accuracy. That is, the accuracy of the aggregated model surpasses that of the individual trained local models. This shows that the aggregation of models results in an increase in the performance, and we hypothesize that by saying that the aggregation provides a regularization effect since no client models overfits on the local dataset, and hence the model accuracies improve on aggregation. We also observe that the simple CNN exhibits higher accuracy than the comp VGG, since the former has a more number of parameters and is able to learn more complex relationships in the data. We further notice that the model learned with 10 clients reaches a particular accuracy faster than the model trained with 40 clients. This is because since we are dividing the same data set among 40 sets for 40 clients and into 10 sets for 10 clients, each client in the former setup gets lesser number of points, and hence the model did not learn effectively. However, lesser data points means that the average global round time for the models should be low, which we do observe. After the successful transfer of the signed learning asset, the receiving network can use weights to train a learning model on possibly a different data set. However, hence we test the efficacy of the transferred weights through a transfer learning task. We first test the transfer weights of the model on simple CNN itself. The transferred weights acts as an initialization, with the task being image classification but with CIFAR 100 dataset. As a baseline, we have trained the simple CNN model from scratch with random initialization. We notice that initialization with transferred weights perform better than the model learned from scratch, and also the performance resonates with the results that we have observed earlier. That is, simple CNN performs better when it was initialized with transferred weights trained on the model via FL setup of 10 clients than when the initialization was done with the weights transferred via FL setup of 40 clients. Now, how will transfer learning work on an augmented model with few base layers remaining the same as SimCNN, but a few more convolution layers added as a head layer? And on a similar note, we again observe that similar phenomenon, that the model initialized with transferred weights perform better than the model learned from scratch, and the relative performance among the different transferred weights hold here as well. Thus, the experiments mentioned above establishes the validity of the cross-chain transfer module and shows that the transfer of weights produce influential initialization variables for transfer learning. The only remaining task is to measure the transfer overheads. First, we report the time it takes to create the asset from the model weights and enter them into the blockchain after fragmentation. We observe that the asset size and the asset entry time scales up linearly with an increase in the model dimension as expected. However, we have observed that the time taken to enter the asset into the ledger by the FL server is around 1 minute, while the global round duration is at least 3 minutes. Therefore, the POFT prevents any contention since an asset will be entered before the asset for the next round arrives, and the clients can avail the latest version of the global model well before an updated version of the same is generated. The transferring the cost includes the retrieval time at sender, the signing time, and the verification time. We have tabulated the values for 4 models in the table, and we see that the transfer time of the asset steadily increases with increasing model complexity. However, unlike the trend in previous slide, the cost of the transfer overhead scales slightly faster than linear. A total of above 4 minutes is required to complete the transfer procedure for a resident model, including the retrieval, signing, and the verification at receiving end. So thus, instead of a simple HTTP post request response model, if we have a separate retrieval threads catering to each transfer request, it would help in concurrent serving of the request. But we have kept this for further studies. So thus, as a conclusion, we have developed an end-to-end framework enabling cross-silo decentralized federated learning over blockchain networks. The framework can learn a model and store it in a blockchain, which can then be transferred to the other blockchain networks in a verifiable and auditable way on demand, thus increasing the scope and efficacy of the model training over multiple networks with rich and diverse training datasets. PFT uses parameter embedding to store the model state in the form of learning asset into the ledger, which can be verified independently without depending on the asset from the previous version's global model. PFT does not explicitly expose the dataset to public space, thus eliminates the possibility of model poisoning. And by our experiments, we have shown the efficacy of the transferred weights and the feasibility of the transfer mechanism. Thank you.